Assalamu alaikum everyone. This is the second lecture of the insulated cables. Today we'll be calculating the capacitance of a single core cable. Let us consider this as a cable where this is the conductor. From this point to this point is the insulation over the conductor, and this is the sheath. From this point to this point is the radius of the conductor, and the capital R, that is from this point to the inner part of the sheet, is the this is the small r, this is the capital R, and this is the dielectric as I have told you earlier, and this is the sheath. Let us first calculate the electric field intensity at a distance x from the center of the conductor within the dielectric material. We know that G is equal to Q by 2 pi epsilon x, where G is the electrical field intensity at a distance of x. Since here it comes out to be x, it means it is at a distance of x. I'll explain this a bit here. This is an infinite long conductor whose linear charge density is Q, coulomb per meter. Here also you can see that Q is the charge per length, that's coulomb per meter. We're assuming it contains a charge of Q per length. Here also I am assuming the same, just to derive it accordingly. We want to find out the electric field intensity at a point P, which is at a distance x from the conductor. So these are the different electric field lines which are coming readily outward from the conductor, from this side also and from this side also. Okay. And to calculate the electric field we use the Gauss law, and I have used a Gaussian surface, cylindrical Gaussian surface, whose radius is x and whose height is equal to L. So by using the Gaussian equation, closed integral of E dot ds is equal to Q encircled by epsilon naught, where Q encircled is the total charge enclosed by the Gaussian surface. In this case, that is equal to Q into L, because Q is the charge per length and this cylinder has a length of L. Total charge enclosed will be equal to Q into L. Okay. One more point. Now we calculate first E dot ds. E dot ds will be equal to E ds cos of theta, where this theta is the angle between the electric field E and the area vector of ds. So here there are three surfaces. One is the circular surface, which is the end of the cylinder. This is also the other end of the cylinder, and the other one, which is the curved surface of the cylinder. You will see that the area vector ds of the curved surface and the electric field, they are parallel. That means that angle between these two will be equal to 0. That means the cos theta will be equal to 1 will be equal to 1. So E and ds will be parallel, cos theta will be equal to 1. So E dot ds cos of theta will be written as E dot ds. Since the area vector for this is perpendicular to this area, this ds and electric field, that is this, will be perpendicular. So cos theta for this surface and for this surface will be 0. So we are neglecting them. So E dot ds will be EDS, and it will be equal to QL, that is charge enclosed divided by epsilon naught. Similarly, E ds will be equal to QL divided by epsilon naught, because E is constant at x, every point at x on this line on the surface of the cylinder. So ds is the curved surface area of the cylinder, that is equal to 2 pi x into L, equal to QL by epsilon naught. E is equal to QL divided by 2 pi x into L. L and L will cancel out along with epsilon naught. So it means this E will be equal to Q by 2 pi x epsilon naught volt per meter. This is the actually unit of the electric field. But usually here we don't use E, we use the letter G. That's why I calculated this, or we can say I derived this for you so that you don't have any problem. Here is the same equation. G is equal to Q divided by 2 pi epsilon naught x volt per meter. Here we can use the epsilon because we may be using some medium like dielectric whose epsilon r will be greater than 1. As we know that this voltage at any point will be this actually voltage gradient. Voltage will be the integration of the or integral of the electric field, that will be equal to q divided by 2 pi. Electric field is g, that will be integral of g dot dx. So q by 2 pi e integral from r to r 1 by x, that is equal to q by 2 pi e ln of r by r. This is very simple. Again its unit will be volt. Hence the capacitance between the core and the sheath is given by C is equal to q by v, that is equal to 2 pi epsilon divided by ln of r by r, and the unit will be farad per meter because in this case q is coulomb per meter. That's why we get the here farad per meter. Now from equation, this equation 3, from equation 1 and 2, that means this is one equation and this is equation 2. G is equal to this value and V is equal to this value. So we will get G is equal to V divided by x ln of r by r, that is the potential gradient at a distance x, at a distance x, because in this case, in these two equations, the earlier equation that was this, G is equal to 2 pi epsilon 0 x, I replace this 2 pi epsilon 0 with, sorry, q divided by 2 pi epsilon 0 with V divided by ln of r by r. These two equations you can do it on your own. So this is the potential gradient at x. Now we want to see what is this potential gradient. Sometimes it's also called as dielectric strength at x is equal to r. We want to see its change from the surface of the conductor up to the inner surface of the sheath. At surface of the conductor x will be equal to r, so there the dielectric strength will be maximum because this r will be definitely the minimum value of the x. So dielectric strength or potential gradient will be maximum at the surface of the conductor. Minimum dielectric strength will be at x is equal to r because x has a maximum value of r. We are changing x from small r to capital R. In that case, G minimum will be equal to V divided by r ln of r by r. Okay? In this case, when we divide these two equations, that means G max by G min is equal to r by r. This is actually the variation of the potential stress from x is equal to r to x is equal to capital R. You will see that it's maximum at x is equal to r and it will be minimum at x is equal to capital R. I hope you understood this. I will stop here. I will go ahead in the next class.